Welcome back, pre-calc students. In chapter 2, we talk about functions. The first part is what is function, graph of a function, getting some information from graph. Those are very elementary. And if you go over to 2.6, now we are talking. There will be some difficult stuffs there. Okay, let's begin with 2.1. What is a function? And here is a nice illustration of a function. In figure 4, we have two sets, set A and set B, and elements of set A is being assigned to elements of set B. That kind of assigning is a function, but there is a bit of a rule. It's okay to have two or more elements of set A being assigned to the same elements of set B, but not vice versa. Every element in set A must be assigned to one and only one element of set B there. Kind of like you cannot be in two different places at the same time. It's okay for two or more people meet in the same place at the same time. So it's okay to have two or more dots in set A is assigned to same point in set B. And there gotta be some example. Yes, here's an example. F of x equals x squared plus 4. If you plug in x equals to 1, or if you plug in x equals to negative 1, you're gonna get the same function value. 1 squared plus 4 is 5. Negative 1 squared plus 4 is again 5. So two different x values in set A, which we call domain as a matter of fact, is being assigned to the same number, 5, in a target. That kind of thing is function. And how to get a function and then how to calculate, those kind of things are discussed here. And then in some cases you'll have to find out a domain of function where domain is not explicitly given. In that case, there are three things to remember. Denominator cannot be 0. So here in this example, f of x in the middle, in the center of the screen, we have 1 over x minus 4, right? So denominator, x minus 4, cannot be 0. So what do we have? We have to exclude x equal to 4. So all x is okay except for x equal to 4. So that's my domain. And if you look at g of x, which is square root of x, inside of the square root is always non-negative. So x has to be greater than or equal to 0. 0 is okay, square root of 0 is 0, so that's okay. But square root of, say, negative 0.00001, still no. Here are more examples. In example 6, find the domain of each function. In part A, you have to set the denominator equal to 0 and then exclude those numbers. And problem B, you have to set the inside of the square root greater than or equal to 0, which becomes a quadratic inequality. And C, well, we have to do both. T plus 1 has to be greater than or equal to 0, but also it should not be equal to 0 either. So T plus 1 is strictly greater than 1 for C, and just do those problems using standard technique, and we have these kind of solutions set. A, B, and C. I'll leave the details to students and then just resume our discussion with my notebook here. And what is a function? Alright. Terminology. Domain, target. Starting set is domain. Target is target set. Range is part of target that has function value, and so on and so forth. Okay. Evaluating a function, okay, and plug in x equals h, and we have that. Plug in a plus h, for example, we have to plug in a plus h in place of here and there. So we have this expression, which is totally fine with me. But if somebody asks you to simplify this, like for example, this WebAssign is asking you to break up all the parentheses, and you have to algebraically manipulate it, express something like that. To me, the first expression is fine. How about the third one? Well, you have this and you have that, so subtract one from the other and divide by h, that's it. And you can actually do something like that. The numerator is f of a plus h, as you did before, minus f of a, and denominator is just h. And then some simplification, subtract, and then constants are gone, and simplification, we end up with something like that. And then do you see cancellation? All the terms in numerator has h, at least one h in there. Denominator is h, so after cancellation, denominator is gone. We have something very simple. And this kind of computation is called difference quotient, sometimes Newton quotient. It is very important as calculus, but here in pre-calc, actually minor deal. So we talked about it, we discussed it. Okay, let's move on. I'm not going to write any exam problem like that here. I'm doing that for maybe some advanced students who want to remember this when he or she takes calculus. Well, here's another comment for domain. Denominator should not be 0. Inside of the square root should be non-negative. If you have a logarithm, then logarithm inside of logarithms should be strictly positive. But we're going to deal with logarithm later in chapter 3, maybe 4. So for the time being, you can worry about only the first two. Let's see. Do we have some nice domain problem? Okay, here are some. You have to set denominator equal to 0 and then expunge them out. Here we go. X squared minus x is equal to 0, which means that is equal to 0. We get x is 0 or 1. So we have to expunge that. X is not equal to 0 and x equals not equal to 1. Throw those away. Then I have everything except for left hand side of 0 between 0 and 1, and then everything right hand side of 1. Actually, this turns out to be a graph of that function, and as you can see, x equals to 0 and x equals to 1 are vertical asymptotes and not part of the graphs. How about this problem? 9 minus x squared. The inside has to be greater than or equal to 0, so we end up with a quadratic inequality. And 9 minus x squared is greater than or equal to 0, so it's equivalent to say x squared minus 9 is less than or equal to 0. So after factorization, do the sign analysis, and you get negative 3 to 3 inclusive. Here's a graph of that function, and from negative 3 to 3, we have this half circle. And unlike the previous situation, we had vertical asymptote. The graph ends abruptly at negative 3 comma 0 and positive 3 comma 0. That's because y coordinate is valid when x is equal to 3 or equal to negative 3. Square root of 9 minus 3 squared is square root of 0, so that's 0. So y coordinate is well defined. Same for negative 3. Logarithm, okay, if you remember logarithm, here it is. 9 minus x squared is strictly greater than 0. So x squared minus 9 is less than 0. We can solve similarly, and you get negative 3 to 3, this time excluding the endpoints, and see the difference. In this case, we have abrupt ending at x equal to negative 3 and x equals to 3 at specified y coordinate values. So x equal to 3 and x equal to negative 3 were valid numbers. So the domain was negative 3 to 3 in interval notation, like that. But look at this graph. We have vertical asymptote at x equal to 3 as a matter of fact. So x equal to negative 3 and x equal to positive 3 are not allowed. So we have to have an open interval, kind of like that. If inside is more complicated, then, well, we'll have to consider those kind of things too. Okay, how about some piecewise defined functions? I got this example from our textbook, but it kind of goes like this. X is less than 40, we have a horizontal line, constantly 39. X is greater than 40, we have, well, y equals to, come on, how do I, okay, that function, which is linear, so we have something like that. But we can consider even more complicated case. And if you use this Mathematica, then you have this piecewise command to get appropriate function. But in reality, if you use alternative source, maybe I'll better show you. Okay, the very first one, and then let's calculate. No, not that one. Where's my Mathematica notebook? 39, and then okay, that. All right, I see. So y equals to 39, and then y equals to, and then that's 0.2 x minus 40. Okay, and then I can ask this calculator to produce both, and then looks like I better scroll out in order to get something, and around 400. Okay, we have did I do this right? 400. Okay, 400. Okay, that looks better. Zero 0.20 x minus 400. Oh, 30 plus 39 plus. Okay, I forgot that one. Okay, that must be right. Okay, here's the graph. If I put those two, and then here you can use your brain. When x is less than 400, less than or equal to 400, horizontal line. So the red line segment, red line here, and then greater than 400, then this tilted line, this one over here, which I highlighted. So we have tilted line blue, and you can get your graph, piecewise defined function, with the help of grapher like this. Just draw everything in the same viewing window and simply take appropriate branches using your own brain. That's more convenient than creating XY table and things like that. If you use high-flying software like Mathematica, then you can do something like this: piecewise defined function with this piecewise bracket command, but it's a little bit difficult to use. Okay. Next, let's talk about graphs. And graph of a function must follow something like vertical line test, kind of like this. From this, you can see that only the third graph, this green graph, is a graph of a function, because given x coordinate value, only one and exactly one y coordinate value must be assigned, just like you cannot be in two different places at the same time. Blue and red are not functional. Green is. That's obtained by so-called vertical line test. Even function and odd function. Let's see. Odd functions have symmetry with respect to the origin. Even function has symmetry with respect to the y-axis. In this particular case, red and green graphs are odd function. I don't see even function in this particular situation. One-to-one function, that's something we'll have to discuss way back in 2.7, but it's a graph problem anyway, so let's discuss it. And let's use horizontal line test, because it has to be a graph of a function, so it passes vertical line test. But also, for given y coordinate value, only one x coordinate is assigned. So draw a horizontal line, and you have to have only one crossing. And if you can see this, blue and red graphs are one-to-one functions. They pass horizontal line test. Green one fail. It's a graph of a function, yes, but it is not one-to-one. There are multiple y coordinate values assigned to a single x coordinate value.